Here's an example for a hypothesis test for a variance. We're going to use the Chi-squared distribution. In this example, we have the number of carbohydrates found in a random sample of fast food entrees is listed below. Is there sufficient evidence to conclude that the variance differs from 100? Use alpha equals 0.05, and we have 10 data points: 53, 47, 46, 38, 39, 73, 43, 39, 30, and 41. And you're going to want to put those numbers into your calculator or into Microsoft Excel so that you can find a standard deviation a little bit later on. First, we should set up our hypothesis statement. So when we set up our hypothesis statement, we're looking at our null and our alternative hypothesis. We are looking at a statement about a variance, and the symbol for a population variance is sigma squared. And we want that it differs from 100. And the differs is the not equal sign, and it's not allowed in the null hypothesis. So we're going to have the equals 100 here, and then the alternative hypothesis in H1, we will have that the variance does not equal 100. So our claim is going to be in the alternative hypothesis. So variance differs from 100. So this indicates a two-tailed test using the chi-squared distribution. And there's a couple ways to do this. We're going to actually do both the critical value method, and the p-value method. So let's do the critical value method first. Really, it doesn't matter necessarily which order that you go in here, but I'm going to find the critical value next. And in this step, we're looking at a sampling distribution that's a chi-squared. So 0 is where we start, and it's skewed to the right. And we have a two-tailed test. That means we have 95% in the middle, and these two critical regions here would be alpha. Alpha was 0.05. That area split up into two tails. 0.05 divided by 2 is 0.025. So each tail here has an area of 0.025, leaving 95% in the middle. The 95% is 1 minus the alpha. We need to find these two numbers on the chi-squared distribution that give us that middle 95% area. We can use our table for this. You could also use your calculator, and that's what I'm going to use. So we're going to use the program called inverse chi-squared. So sorry for the screen here. I won't be able to see it really well, but we're going to go into the program key, and I'm going down to this program called INVCHI2 inverse chi-squared is what that stands for. If you're on a TI-89 calculator, you actually have this one already built into your stat app, so you don't need an extra program to run this one. If you go into the apps button called Stat List Editor, and then under F5 is your distribution menu, and there's another drop-down menu called inverses, and then you have your inverse chi-squared here. So in the program over here, to hit enter brings it back to the main screen. Hit enter again will activate the program. And it wants, in this one, the area to the right of wherever we're trying to find. So we have to do two of these. So let's start with this right-hand one over here. And the area to the right of that point would be 0.025. And I hit enter, it's going to ask me for my degrees of freedom. Our degrees of freedom would be the sample size minus 1. There was 10 data points, so we would have 9 degrees of freedom. And it's going to think in here. On the TI-89, when I type in 0.025 and the 9, it's actually going to give me the left-hand value, so opposite the 84. The TI-89 is doing the area to the left of the point. So when I typed in 0.025, it gave me a different number than my TI-84. It gave me 2.70. And on this one is 19.023. So how you just flop those around to get the other area. So if I start the program over again, so do program inverse chi-squared, but this time think about how much area is to the left of this point here I have this 95% plus this 2.5% would be a total area of 0.975, or 1 minus the 0.025, and then the same 9 degrees of freedom. And then you would get the 2.70 that the other calculators. And then on the 89 you do the reverse. So when you put in 0.975, you're going to get the 19.023. Those two numbers are equal value. You can take those off of your chi-squared distribution table as well. Anytime our test statistic falls in the shaded area, you would reject the null. And anytime the test statistic falls in here, you have do not reject H0. So let's find the test statistic. And if you're having a hard time on an exam trying to figure out what formula to use on these, I have this guide here, this flow chart. You can look at proportions, means, variances, or standard deviations. And in our hypothesis statement, we were making a claim, a conjecture about the variance. So I'm going to start over here on the left with variances. Then ask yourself, do I have one sample or two samples? I only had one sample given. And TS stands for test statistic. So this is just reinforcing what hypothesis statement that you use and what test statistic you use, and then what program that you can actually use for a shortcut key in your calculator as well. This is your formula. So we have chi-squared equals n minus 1 times the sample variance over the hypothesized variance. So n minus 1, we calculated that was 9. S squared we haven't calculated yet. So you need to do just a simple 1 var statistics on your data. So in my stat menu, I've already put in my data points, enter them in. I go to stat, and then I go to calc, and then 1 var statistics. This is F3 if you're working on the TID9. I'm sorry, F4 on the TID9 is your calc menu, 1 var stats. And we're always going to want to pull the SX off here. This is a sample we just put in, not this population. So 11.6376, got at least 4 decimal places there. And that was S off the calculator, so we'll need to square that. The standard deviation squared is the variance. And the sigma not squared is the variance that comes from your hypothesis statement. So if I look back in here, under my null hypothesis, the variance was equal to 100. Variance has already been squared, so you don't square it again. So if you put that in, calculate it, it comes out to be 12.189. And then as far as our number line, where does that fall? 12.189 is here, so we would have do not reject the null. And then the summary going from there would be that there is not enough evidence to support the claim that the variance in carbohydrates for fast food entrees differs from 100. Now, if I was doing this on the program to see those same results, it actually gives you a p-value method. So if you were doing it long way for p-value, you would first find your test statistic of 12.189. And the p-value is how much area is to the right or bigger to that right-hand tail times 2, because this is a 2-tailed test. So I can use my chi-squared CDF and think about the lower limit as my test statistic and my upper limit as infinity and 9 degrees of freedom. And what that gives you is just the area in the right-hand tail. You would still need to multiply that by 2 for a 2-tailed test. If you were doing a right-tailed test, you'd be done. If you were doing a left-tailed test, you would actually reverse those and do negative infinity up to your test statistic. And then for a 2-tailed test, you're going to find either one of the tails that you're in times 2. So if I go back in here, this is under my distribution menu, F5 in the stat app on the TID9, or right under here on VARs. And it's down a little ways, and it's called the chi-squared CDF. Make sure you're using the CDF, not the PDF. And it's always lower, upper, and then degrees of freedom separated with a comma. So 12.189, comma, infinity. They have the infinity button on the 89, but not on the 83 and 84. So you can just put in a really big number for your infinity. You can also do the 1E99. That also works well. Comma, and then your degrees of freedom, and we get 0.2021 9 approximately. But that's just one of the tails, and we have a two-tailed test, so I'm going to multiply that by 2. So our p-value is going to be 0.4057. Anytime your p-value is bigger than alpha, you do not reject the null. So this 41% approximately is much bigger than 5%, so we would have do not reject H0. Same thing we got with the traditional method. Now, all of this is in a shortcut key on your program. So if you're looking on the program that I installed on your calculator, if you don't have the program, then of course you can't do it this way, but if you go into your program menu, and it's down a little ways, it's called SDINFER, or if you're on the old 83, not the plus, but the real old 83, it might say SDINFER 83. But you want the SDINFER, standard deviation inference is what that stands for. And then you're going to hit enter to start the program, and it's going to ask you your value for your sample standard deviation. Now to catch that up on the TI-89 users, so if you're in a TI-89, to get to your program, you're going to actually go back to your home menu first. Oops. So I'm going to hit home, make sure that you're in the home button. I'm going to hit catalog. Up on the top under F4, you're going to hit user defined. And then SDINFER, you might have to scroll down a ways. It's going to be alphabetical. Here's your SDINFER. And when I hit enter, that puts it out with a starting parenthesis, and you need a closing parenthesis. So type in a closed parenthesis, then hit enter, then it will start your program off. So then you're going to type in your value for your standard deviation, which was this number here. The sample standard deviation was 11.6376. Again, go out at least 4 decimal places. Hit enter, or scroll down if you're on the 89. The sample size was 10. Make sure not to put the degrees of freedom in, but the actual sample size. And then it's asking you what you do. So this is back for a confidence interval for a standard deviation. This one is a confidence interval for a variance. This is a hypothesis test for either a standard deviation or variance. It's in the same menu. And we have a left-tailed, two-tailed, and right-tailed test. So you need to look at the alternative hypothesis. What sign do you have in that? And we have a not equal sign, so I'm going to choose the not equal one. Then it's going to ask me for, be careful here, the sigma, not the sigma squared that's in our hypothesis statement. So we need to go back here and think about what would be sigma. It would be the square root of 100. You could probably do that in your head too. You might want to even do that separate and write it down out to 4 decimal places, but you can also just write in square root of 100 and it will automatically know that that's going to be equal to 10. It not only returns the test statistic and degrees of freedom, but also the p-value. So note here the 12.189 is what we found here. And our p-value was our answer here. So it does a lot for you. You can do both methods and check your answer.